record from this point onwards. We can start from this. Okay, thank you very much. Okay, on the chat you have something. Okay. Okay, then shall stream. This is video lecture 2. We have done this one. And from this point, I think we can, you have drawn this one to refresh your memories. I'll show the problem. Then we can have maybe that couple of months ago we have done this one, or couple of months ago, this February we did it in October. Okay, these are the questions we have to discuss, and we finish this first question. And after that, this electrical control systems, I think we have done this one also. And this is the one, the last we have done. One step in manufacturing process, and we have installed flow rate sensor, pressure sensor, and temperature sensor. 3 sensors are there. Then we have 2 dangerous conditions. And one first dangerous condition is flow rate and pressure are low. That is one first dangerous condition. The second dangerous condition is that pressure and temperature are high. And those are the things. And then this is flow rate and pressure are low. And this is first condition. And this is second condition. Okay. Then based on that, considering these ones, we have written our equation. Then we have to draw the circuit. Okay. To get you refreshed, that I think I can draw this one. Then we have 3 sensors there, F, P, T. Then let's make F bar, P bar, and T bar. Then try to make the first term. First term is F bar, P bar, T bar. Okay, this is P bar, T bar. Okay. Then we make a second term. Second term. It's a mistake. This is F bar, P bar, T bar. The second one, F bar, P bar, T. Okay. And here, this should be T. We need F bar, P bar, and also we need T. T we can take from this point. and we need T bar and F bar. Again, different color. Here we need F bar PT. T is already here. Then we need P. And F. Last one. PT. Then here we have T. This is P. And we need F. Okay. Then we have to combine these four together to make M. Okay, this is the circuit we can draw as the solution of this problem. I think now you can remember all these things maybe. Is it okay? Okay, if you're okay with that, then we can do okay, then we can try a different question. Okay, we did this one. Shall we try? This is the last one we are going to try, but it's a different type of question. But so far, I think we have done this point, and this is some kind of extension that what we have initially discussed. Then we have three door sensors, and we have to develop a circuit to sound an emergency bell, then these are the 4 dangerous conditions. Then after that, we came to this question. Then again, this question, there is no lot of information available, but we have to extract the idea from that question. Then we have to develop the circuit. Again, we have 3 sensors and the condition is there. And this third one is a different type of question, but the 2 different conditions are there, but in with verbal format, and we have to extract the conditions from the text. Okay. But all the questions are somewhat similar type of questions, because at Y we have multiple inputs and single output. But in this question, we have multiple inputs and multiple outputs. Because of that, this is a pretty important one, because we haven't done this type of question before. Then shall we try this? To try to understand the question that this circuit receives 2 binary inputs, A and B, and you can see that both A and B are single bit binary numbers. Okay, the meaning is A is a single line, B is a single line, because they are single bit binary numbers. And we are giving these numbers to the circuit. Then circuit will compare these 2 numbers and produce these outputs. Whether A greater than B, it will produce one output. A equals B, another output, and A smaller than B, it will generate another output. Then 3 outputs are there and 2 inputs are there. Shall we spend a couple of minutes and try to start this up? Okay, then we have to draw the block diagram first. Then okay, we have two inputs. First one A, the other one B. And we have three output lines. First one, shall we take, this is giving A greater than B when these two numbers, according to the condition of these two numbers, A greater than B, this will indicate it. Then the second one, A equals B. Third one, A is smaller than B. But for all these things, that shall we take a single letter? Shall we take, this is P and this is Q and R like that? Then we can make a truth table. We have two input columns. A, B. These are the four combinations we have. And P, Q, R. What is P? A greater than B. P is A greater than B. Okay. When P is A greater than B, here A equals B. A equals B means Q. Then here Q is 1. These two are 0, 0. This one is smaller than. This condition is A smaller than B, then R is 1. Here A greater than B. Then this is 1 and these two 0, 0. This one again A equals B. Q. Okay. Then how many output equations we have to write? How many output equations?
3.
3. Yes, exactly correct. Three equations we have to write. Why? We have 3 output lines. Then for P, we have to write 1 equation. To write P, then we have to consider this column. Okay, then one question is asking that how to prepare this truth table. Actually, that's is something like that. Here we have to produce 3 outputs. 3 outputs are A greater than B, A equals B, and A smaller than B. These are the 3 outputs we have to produce. Okay. Then whatever the thing that these are the 2 numbers that we have to consider, these 2 numbers A and B are the single bit numbers. Then we have to consider the value of these numbers. Okay. Now at this condition, first when you consider the first combination, value of A is 0, value of B is 0. Then we have to compare these 2 values. Then 0, 0. 0, 0 means A equals B. That's why Q is 1. When A equals B, through Q, it will be indicated. Then Q shows us 1. Why 1? Because A equals B. Then during that time, P is 0. R is 0. Why? Condition satisfied. A equals B, not A greater than B or A less than B. Because of that, P is 0, R 0. When you come to the second combination, value of A is 0, B is 1. Then B is greater than A. Okay. Then R should be 1. what is R? A smaller than B, then that is O. Then the third one, A greater than B, A1, B0. Then P should be 1. The last one, 1, 1. Then A and B both are equal. Okay. Then shall we write output equation? Oh, to write P, we have only single one. This is, sorry. A, B bar. Then Q. So Q we have 2. Okay. So this Q we have 2. Okay. Then we can write Q considering this one. This is A bar B bar plus this one. This is AB. The last one. This one. This is R. We have to separately consider these 3 columns to write 3 output equations. Here also we have only single one, that is A bar B. Now starting from 2 common points, we have to draw the circuit. These are the equations. Then we have this is A. We need A bar also. This is B. We need B bar also. Sorry. Okay, first we make first term. First term is A B bar. This is P. P means A greater than B. Second one, A bar, B bar. Then AB. Okay. Okay, this is the circuit. So you can see we are starting from these 2 common points, and finally we will have these 3 outputs. The block diagram shows it. We are starting from these 2 common points. These are the 2 inputs, and we will be ended up. It will be ended up having these 3 lines. Yeah, and this is the circuit. It's okay. If you are okay with this understanding of these problems, that if you are okay with this type of problems, and finally that you have to draw the block diagram, and prepare the truth table, then extract the output equations. Okay. Then based on the output equation, you should be able to draw the circuit. If you are okay with these 4 steps, then you are a digital designer now. You can design digital circuits, but we are not considering the implementation part. We have to go to the lab for the implementation. But here we are not going to do that one. But up to the designing part, you can do now. Is it okay? If you are okay with, can you please explain how you got the equations again? These equations, I think we have written these equations considering these 3 output columns. To write P, we have to consider P output column. To write Q, we have to consider Q output column. To write R, we have to consider this output column. It's something like that, that you may remember this problem. How do we do this one? Now, this is the one, this is the problem, and we develop this truth table, we prepare this truth table, and here we have only single output column, M. Then to write equation for M, we have to consider this one, and 4 ones are there. We'll consider these 4 ones to write output equation for this M, but here we have only single output column. Then if you have single output column, we have only single output equation. Okay, that's what here we have. In the previous problem, we have only single equation. Why? We have only single output column. Because of that, we are starting from 3 points, 3 inputs, and it will be ended up having single output. Then after that, when you come to the today problem, then here we have 2 inputs and 3 outputs. Because of here we are having 3 outputs, we have 3 output columns. For each and every column, we have to write output equation. Okay. Then here we have written 3 output equations. Then we have to draw the circuit having 3 outputs. Okay. Starting from A and B, we are making P first, Q, and then R. We have 3 output points. Is it okay? And another question is asking, sir, will we be creating a digital circuit during practicals? Actually, for your module, this module, you don't have practicals. Because of that, the implementation parts we are not going to do. But anyway, it's another step that if you are having some kind of equipment, then power supply and some kind of couple of very few equipment, then you can develop, you can implement the circuit also. But in your scope, in your this module, in your scope, you don't have lab classes and you are not going to implement this one. Should we write the output equation considering only one? Yes. We have to write output equation considering these ones. It's a good question that if you don't have a misunderstand, I can tell something else also. But this is additional to your, this is additional information, okay? Please don't do it, but if you want that you can do it, it doesn't matter. But if you have that fully understanding about this one, you can do it, okay? But we are writing equations for what? We are writing equations for P. We are writing equation for Q and R. To write equations for these P, Q, R, what we are considering these ones. For example, you can write output equation considering this one, then this is this one. Sorry, then this is A, B bar. Okay. But if you consider these zeros, can you write output equation? Yes, you can. Then that is for P bar. When you consider 1, you are writing output equation for P. When you consider zeros, that is P bar, inverse of P. Then what are the terms? A bar, B bar, A bar, B, and AB. Then if you want, you can use this equation, but your drawing should be P bar. At the end of the circuit drawing, you can't write here P. It should be P bar. Okay. But don't get confused if you don't understand this one. But only writing equation for P, that is enough. This is additional information. But if you want, you can write equation for P bar also. Then if you are going to write equation for P bar, you have to consider zeros. But here we are considering ones. Then we are writing equation for P, Q, R, not P bar, Q bar, R. Ajay, is it okay? Did you understand? Okay. Then if you don't have anything, any other question, then shall we move into the next section? Now, if you are okay with all these 4 steps, and if you are not having any questions regarding these sections, then that means that you have done all these things and you have the knowledge to design digital circuits. Then you can do it. But we have to go a little bit beyond that one also. To do the advanced designs, we have to add another set of tools. Next section is targeting that one. Shall we go? Okay, then this section, we are going to add another set of tools to do some kind of advancement of our designs. Then here we are going to learn some kind of theorems. Okay. Then first theorem is it's actually law, commutative law. This commutative law says us it has 2 parts. First part, it says AOB equals BOA. What does it mean? When you take O gate, and if you use these 2 terminals to give A and B, and you will have a result. It's totally identical to if you interchange these 2 terminals like this, no problem. Same results you will have. You may wonder that why is it necessary to tell this one, but yes, this is what law says. When you are free to do that one, you can do it. The second part of this one is it's targeting AND operation. A and B equals B and A. Then it's for AND gate. It's almost same thing you can do by interchanging the terminals also. But what is the summary of this one? What is the idea behind this? it says us order of variables. Order of variables. Doesn't matter A, B, or B, A is not important. That's what it says us. The second one, associative law. Again, it has two parts. It says us, if you take this one, it equals to this. What is the meaning? You can take 3 input OR gate, and do this. The same thing you can do this way. And also and if you have 3 input gate, straight away you can do this one. But assume that in a situation that if you don't have 3 input OR gates and you are having 2 input OR gates, then you can combine two input OR gates and do the function. Okay. Again, it has second part also, that is targeting AND operation. ABC equals this way and also this way. I'm not going to draw the diagrams, but you can understand it. What is the summary of this one? The grouping of variables. Grouping of variables. If you group these variables, it's not important. This is a summary. This is a simple idea behind this theorem. Okay. Third one. Distributive law. It's another useful law. It says us if you have equation like this, if you want, you can expand it. This is allowed. You can do it. Here, how many gates do you need to make this term one AND gate, to make this term another AND gate, 2 AND gates, and to combine this one OR gate. To make this one, you need 3 gates. Okay. Excuse me for 1 minute. Sorry. Then here we have to use 3 gates. But here to combine this one OR gate, and to make this one 2 gates. It doesn't matter. Same results you can obtain. Is ACB also possible? Yes, yes. This one is also possible. The question is asking that is it possible this way also? Yes. So that from the first law, the commutative law, it says that order of variable is not important. Then if you write this one, this ABC, if you want that, you can write this way also. The order of variables is not important. Because of that, this is allowed. And after that, this one, the grouping is not important, but whatever the way that you can group it, and whatever the way you can have the order, and whatever the way you can have groups, it doesn't matter. This is allowed. It's correct. Okay, the next one. De Morgan's theorem. This De Morgan's theorem also, it has 2 parts. First part says A plus B bar, that is no operation. It equals to this one, A bar the second one says this none. It equals okay. Then shall we try 5th one? It says it's actually principle of duality. It says us any kind of theorem, law, or relationship, whatever the thing, it has a dual. Dual means another face. It's like a coin that you have 2 faces, and when you have one equation, it has 2 faces. Okay, if you have one face, you can obtain the other face by replacing of zeros of that equation to 1, ones to 0, and plus to dot to plus to dot means O to N, N to O. Shall we write it first? Any theorem, law, or relationship has a dual obtained by replacing every occurrence of 1 by 0, then 0 by 1, then Dot means AND operation by plus and by dot. Okay. So you can see this one. It's interesting one. Sorry that some of the disturbances are coming. But anyway, this is the one. Principle of duality. Shall we apply this one? That shall we take this De Morgan's theorem first part? It's A plus B bar equals A bar dot B bar. How can we apply this one? This we can convert this one. This A is there, A should be there, and B is there. This bar is there, and we have to convert this plus. We have to replace this plus by dot. Okay. Then equal signs, this A bar, B bar, and we have to convert this dot to plus. Then what is this? What is this? This is first part of De Morgan's theorem. And when you apply principle of duality to this first part of De Morgan's theorem, what we have received? The second part of De Morgan's theorem. Is it okay? Can you give me a couple of minutes? Okay, we can, sorry, actually, sorry for the disturbance. Because it's a weekday, because of that, that type of disturbances are coming. But anyway, shall we come to the lecture again? Then we have discussed principle of duality. Then the next one, logic identities. Okay, logic identities. Then what do you think about that? Sorry. What is A double bar? If you send same signal through two NOT gates, what will you receive? Yes.
A.
Same thing. Yes, that's correct. Okay, shall we try these ones also? Then next one, what about that A plus A? Then A plus A bar. Then A plus 1. A plus 0. What is the meaning of this one? Then A plus A means that you are sending A here, the other terminal also. You have common these two terminals, and you are sending A. Both terminals are receiving A. Then if, what is this? Then A plus 1. A plus 1 means 1 is variable. The other one is permanent one. It's not variable, it's a permanent. Then what is the result? Can you find these things? And if you are okay with this one, then shall we try to find this one with AND operation also? Okay, what is this? A plus A? A plus A is A. A plus A bar is always 1. A plus 1, again 1. A plus 0, it's A. A dot A, it's A. This is 0. This is A. This is 0. If you have any kind of question, that let me know. Then we can try to do. Third and fourth one, can't we take A as the answer? Third and fourth. Third and this one, A plus A bar. A plus A bar is always 1 because that assume that A is 1. Because if A is 1, because you know that with OR gate, any input is 1, output is 1. Then if A is 1, bar is 0, but 1, A is 1, then output will be 1. Assume that A is 0, then A bar will be 1. Whatever the time, 1 will be 1. A may be 1 or A bar may be 1. Then always it gives 1. That is for third one. That's why it's 1. The fourth one, A plus 1. This 1 is permanent. Here, this is permanent 1. Because of this one, whatever the value A is having, it doesn't matter. Because we have given 1 here. Because of that, is always it's 1. Fifth one, this one A plus 0. A plus 0 means that here this is A and this one is permanent 0. Then output. Assume that A is 1, then output will be 1. Then what about A is 0? Output is 0. Then whatever the value A is having, it will be at the output. A is 1, this is A is output is 1. When A is 0, output is 0. That's why we say this is A plus 0 is A. Is it okay? Yes. And those are the theorems and we have to learn. And now you can take one of these and you can, if you want to, maybe take this one. Okay, what is that? This is A plus 1 equals 1. Shall we apply principle of duality to this one? Then A is A. Then we have to convert this plus to dot and this 1 to 0. Okay, then this 1, we have to convert this 1 to 0. Then when we have A plus 1 equals 1, when we apply principle of duality to this one, we will receive A dot 0 is 0. A dot 0 is 0. This one. When we apply principle of duality, we will receive this one. Is it okay? Okay, if you are okay with these things, then shall we try to apply these theorems and whatever the things we have learned to these equations? Okay. Do you remember the first equation we tried? Let me show that the first problem we have tried there. Show modes. Okay. This detail. Okay, here you remember this one. This is our first example. We tried this one, very simple one, and this was the final equation we got. M equals AB bar plus AB. Okay. M equals AB bar plus AB. Okay, shall we take this one? M equals, this equation is coming from first question. M equals AB bar plus AB. Okay, now using whatever the theorems and laws or relationship or whatever the thing that shall we try to rearrange this equation? How can we rearrange this one? Here you can see A is common from this equation. A is common. Then we can take A out. Then inside that we have B bar plus B. What is B bar plus B? You can see here. This is A bar plus A. Sorry, A plus A bar. What is that? A plus A bar is 1. Then B bar plus B is 1. Then this is our rearranged equation. Have you done anything wrong? Have we done anything wrong? No. All the thing what we have done is that we have applied the theorems we learned. Theorems are the proven ones. Then we haven't done anything wrong here. Then finally, shall we go back to our previous one? And this is the equation we got. And this is the diagram we have drawn as the solution. Here, how many gates we have drawn? 1, 2, 3, 4. But instead of having all these things, the solution is, this is A and B. And this is M. The straight away you can connect here. There is no gate needed. Sometimes it may be a little bit confusing. Okay. Shall we try this one? What is the equation here we have got? This is the one. Okay. Shall we copy this equation and come back here? Okay, this is the equation we are receiving from our second example. Here, A bar, B bar, C bar. Okay. Shall we try to rearrange this equation? Okay. From these two terms, I can take A bar, C bar out. Then B bar plus B, they are inside. Here, what is common? Then I can take C out. Then here, A bar B plus AB bar is common. What is this? This is 1. And this one, this is A exclusive of B. I'll explain this one, why this is A exclusive of B. But assume that for the moment that it is correct. If it is correct, the new rearranged equation is A bar C bar plus C A exclusive of B. See here, how many gates are there? Many gates, but less number of gates here we are using. Okay, then I'll explain that how I can take this one. Then do you remember the exclusive OR gate truth table? This is exclusive O. Exclusive O truth table is here 0, 1, 1, 0. Okay, then 0, 1. Then, okay, forget about that. This is exclusive O. Okay, then assuming that this is F, for F we can write output equation considering this one and this one. This is A bar B plus A B bar. F equals that you can write that, forget about this A exclusive O B, this one here. Considering this as a normal truth table, we can write output equation for this F, that is, then we have to consider these two ones, 1 and 1. Then this is A bar B plus A B bar. But you know that this is equals to A exclusive OB. Then whenever the time that you see A bar B plus A B bar, A bar B plus A B bar, you can write A exclusive OB. Okay. Then same time that I'll tell some other thing also. Okay, shall we consider these zeros? If we write equation using these zeros, what is that? That is F bar. F bar means A bar, B bar plus A B bar. I wrote F bar using these zeros. This zero is A bar, B bar, this zero is A. Now what is F bar? A exclusive O B bar. Then whenever the time you see that A bar, B bar plus A B, you can write A exclusive O, actually A exclusive no. Remember this one. This is very useful. Okay, anyway, that. What do you think about that? If we rearrange these equations like this, what do you think? Oh, this is the original one. Okay. This is original one. And this is our rearrange. Which one is the best one? This is our original one. This is rearranged one. What do you think? Which one is the best one? Which one giving much more flexibility? Here, less number of gates. You can see, because of the less number of gates, the cost is low. And when you implement these things, the space is low. And because of that, we are using less number of gates. The power consumption is low. Lot of advantages are there. Then what do you think? Which one is the good one? The rearrangement. Okay. That is our next lesson we are going to learn. Rearrangement means actually we call this is not rearrangement. We say this is logic equation minimization. Then our new topic is minimization of, we can say like that, Boolean equations. Okay. For this one, we have two methods. The first method is using Boolean algebra. We can minimize equations. The second method is using Carnot method. Using Carnot method, we can minimize equations. Okay, these are the two methods we can use for minimization. And using Boolean algebra, whatever the thing that we have done here, that is using Boolean algebra, we have minimized the equation. This Carnot method is Boolean graphical representation of equation. And these two methods we can have a lengthy discussion the next day. Okay. Up to this point, do you have any question? Okay, if you don't have any question, then shall we stop the class now? Okay, we can stop the class now. Thank you very much for your participation. Yeah, thank you very much for your time. Hope that you have understood everything. And if you have any kind of question that in the very beginning of the next day, I'll ask this question. Okay, be safe and take care of yourself.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Okay, you're welcome.